Good morning, students. Sej Ananda. Continuing our video lecture series of analog and digital communication subject. Coming to the lecture 7, we'll discuss in this about amplitude shift key, ASK, and then the BFSK, BPSK, and DPSK. We'll discuss 4 shift keys over here. These are all the digital modulation techniques. So basically, coming to the ASK, so amplitude shift keying is a form of digital modulation technique in which the amplitude of the analog signal carrier, amplitude of the analog sinusoidal carrier signal is varied to represent the input signal data or the digital data. Mathematically, it can be expressed as having amplitude which follows the massive signal or no amplitude, that is A cos 2 pi FCT for binary 1 amplitude and 0 for binary 0. So where A is the maximum amplitude of the carrier signal and FC is the carrier frequency. Thus, the modulated ASK signal is either the carrier signal for binary 1 or no carrier for binary 0. That simply means that the carrier signal is either on or off, depending on whether the digital modulation data is either binary 1 or the 0, respectively. This is the reason that sometimes amplitude shift keying is also referred to as on-off keying. OOK. This is the waveform of ASK. This is our massive signal. This is the carrier signal. And this is amplitude shift keyed signal. That is, it will, whenever where there is a binary 1, it will follow the carrier signal. And whenever there is a binary 0, it will display no signal. Again, 1 is here, it will display this carrier signal. 0 is here, it will display no signal. So it is continued in this way. Coming to the modulation portion or the generation portion, how it is generated. So this is the basically block diagram of the ASK modulator. For every change in the input data stream, either logic 1 or logic 0 or vice versa, there is a corresponding change in the ASK signal waveform. For the entire duration of the input binary data logic 1, that is high, the output ASK signal is a constant amplitude, constant frequency sinusoidal carrier signal. And for the entire duration of the input binary data logic 0, that is low, the output ASK signal is 0 or there is no carrier signal. So the modulation portion consists of a balanced modulator. A sinusoidal signal is applied to a balanced modulator. And a sinusoidal carrier signal and a massive signal is applied to a balanced modulator, and then it is passed through a band pass filter. These upper and higher bands are rejected, and only a band of carrying the carrier frequency components will be passed, and it will give us the respective ASK signal. Okay, so let me describe this. ASK signal may be simply generated by applying the input binary data sequence and the sinusoidal carrier signal to the two input balance modulator. The digital signal from a digital source is a unipolar non-return to zero signal which acts as a modulating signal input to the balance modulator. The output of the balance modulator is the product of the non-return to zero signal and the sinusoidal carrier signal. The output is passed through a band pass filter in order to obtain the frequency spectrum of the ASK signal. So the basic block diagram of ASK modulator is very, very simple. Similarly, the demodulator block diagram is also very simple. This is the basic block diagram of ASK demodulator. It will consist of a balance modulator and then followed by an integrator. I box it in one. Then a decision device where we set a preset threshold level, which will give the demodulated output or the original massive signal. The received binary ASK signal and a sinusoidal carrier signal generated and by a local oscillator are applied to the balanced modulator. The integrator operates on the output of the balanced modulator for successive bit intervals and essentially performs a low-pass filtering action. Its output is applied to a decision-making device which compares it with a preset threshold level. It makes a decision in favor of the symbol. That is, when there is a signal present, it will output as 1. And when the threshold level is exceeded, when the threshold level is exceeded, it will represent 1, and when the threshold level is not exceeded, it will return the 0. This is how the ASK modulated signal is demodulated, and we get the original message signal at the output. Very basic circuit diagram is here of both. Coming to the advantages and disadvantages, ASK is the simplest form of digital modulation scheme. It is simple to design, easy to generate and detect. ASK requires very low bandwidth. Very less energy is required to transmit the binary data in ASK modulation. Coming to the disadvantages, ASK is an inefficient digital modulation technique, and ASK is susceptible to sudden amplitude variations due to noise and interference. So coming to the next digital modulation technique, that is BPSK, stands for binary phase shift keying. Earlier in ASK, amplitude is varied or passed or not passed for the digital binary input. Here, a phase is changed for a digital binary 1 or 0. So let us discuss. In BPSK, the phase of the sinusoidal carrier signal is varied in accordance with the binary value of the binary information data bit to be transmitted. BPSK is also known as biphase modulation or phase reversal keying. Mathematically, it can be expressed as for logic 0, there will be no phase shift, and when logic 1 is present, there will be a phase shift of 180 degrees. This is the waveform of the BPSK signal as we have given this input. For 1, it will follow. For 0, it will have a phase shift. Then again 1, it will have a phase shift. For 0, it will have normal. For 1, it will again have a phase shift. In binary phase shift keying, for binary 0, 0 degree, and for binary 1, there is a 180 degree phase shift, as we have seen mathematically in this expression also. Same is stated over here. When the input binary data changes from 1 to 0 or from 0 to 1, the BPSK signal output phase shifts from 0 to 180 degree or from 180 degree to 0 degree. The time duration is the same as the symbol time duration. Coming to the modulation portion, how this BPSK signal is generated. It is again very simple as compared to ASK. ASK was simple, it is simpler than that. It will consist of only two things. Here the bit stream is coming one of a sequence of ones and zeros, having it will pass through an encoder, and then it will pass through a balance modulator where we will supply the carrier frequency and get the BPSK signal. The binary data sequence of zeros and ones is converted into a non-return to zero signal. Its output is then applied to a balance modulator whose other input is from a local oscillator, which local oscillator produces the carrier frequencies. The output of the balance modulator will be in phase with the reference carrier oscillator phase for binary 1 and 180 degree out of phase with the reference carrier oscillator phase for binary 0. Now coming to the demodulator portion, it is again very, very similar to the earlier ASK demodulator that we have discussed. The incoming BPSK signal is applied to the correlator. Correlator is a combination of a balance modulator and an integrator. I broke that box into one block only containing the integrator and a balance modulator, that is known as a correlator, which consists of a balance modulator and the incoming BPSK signal is applied to the correlator, which consists of a balance modulator and an integrator. The other input signal to the balance modulator is from a locally generated carrier oscillator. The output of the correlator is compared with the preset threshold level using the 0 volt. This is a threshold detector or the decision device, which we have seen earlier in the ASK demodulator also. The decision device will have a preset threshold level. If the value is exceeded from that, then the signal will pass the BPSK signal will have 0 degree phase shift, and if it is low, then it will be have 180 degree phase shift. If the input of the decision device is greater than 0 volt, then the detected output is 1. If the input to the decision device is less than 0 volt, then the detected output is 0. Coming to the advantages of BPSK signal, BPSK has a very good noise immunity. There is a minimum probability of error in reception of digital data. The transmission bandwidth for BPSK is same as that for ASK and less than that of BFSK. The bandwidth efficiency of BPSK is very better. Coming to the DPSK signal, DPSK is same as we have read earlier in this lecture. Not in this lecture, earlier to this in PCM, it is similar to DPCM. DPCM, DPSK are similar. there also we send the difference between the pulse samples, amplitude samples difference is sent. Here also the phase difference pulse is sent. DPSK is an alternate form of BPSK where the binary data information is contained in the difference between the phases of two successive signaling elements rather than the absolute phase. A binary one is represented by sending a signal bit of opposite phase to the preceding one, and a binary zero is represented by sending a signal bit of the same phase as the previous one. So this is the basic and very simple block diagram of a DPSK modulator. It will consist of an encoder or a logic circuit. Here I have used a logic circuit. A delay is used. Then a balance modulator is used, whose other end is having an input, which is a locally generated carrier oscillator output. So let's discuss its operation. The input binary data sequence is applied to the input of the encoder or the logic circuit, such as an XOR gate. As you can see, I have used XOR gate. The other input to the encoder is 1 bit delayed version of the previous data. The output of the encoder is then applied. Encoder or a logic circuit is applied to the bipolar non-return to zero line encoder followed by a balance modulator. The other input to the balance modulator is from a sinusoidal carrier signal oscillator. The output of DPSK signal in which the phase shift depends on the current bit and the previous bit. So here bit is compared and the difference of both are sent. Coming to the DPSK demodulator, which is again a very simple circuit diagram. The received DPSK signal is then applied to a bandpass filter before applying it to an encoder or a logic circuit. The configuration of the encoder is inverted as compared to that of DPSK modulator. The input data is delayed by 1 bit. After passing it through a bandpass filter, it is delayed by a 1 bit interval. Both these signals are then applied to the correlator. Correlator, as I have told you earlier, is a combination of a balance modulator and an integrator. So it is then applied to a correlator. The difference in the original signal and its delayed version is proportional to the difference between the carrier phase of the received DPSK signal and its delayed version measured in the same bit interval. This phase difference is used to determine the sign of the correlator output of each bit interval. When the phase difference is 0, the integrator output is positive. And when the phase difference is 180°, the integrator output will be negative. The output of the integrator is finally compared with the 0-volt preset threshold level by the decision device. And if the input to the decision device is greater than 0-volt, then the detected output is 1. And if the input to the decision device is less than 0-volt, then the detected output is 0. It is very simple. And if you can remember these 4 blocks or 2 blocks or 3 blocks of each of the shift keying modulator and demodulator, its working or operation can be written as easy as it is. Coming to the advantages of our BPSK signals. Advantages are it is simple to implement because the carrier recovery circuit is not needed. It requires less transmission bandwidth. DPSK offers less immunity to noise and interference. And coming to the disadvantages, it has higher error probability and bit error rate because it uses 2 successive bits for its detection. And it requires additional 1 to 3 dB of signal to noise ratio to achieve the same bit error rate performance as that of conventional BPSK scheme. Now coming to the BFSK signals. Sorry. So BFSK is a form of digital modulation technique in which the frequency of the analog sinusoidal carrier is varied to represent the input digital data. It has a constant peak amplitude and phase. And the name suggests frequency will be shift. In amplitude shifting, amplitude is varied. In phase shift and phase is varied. In frequency shifting, frequency will be varied. And how it will vary? It is mathematically expressed as a sine 2 pi f1t and a sine 2 pi f2t. Let's have a look what is f1 and f2t. So this is our input signal. For binary one, the modulated signal will follow the carrier signal. For 0 input logic, it will have a frequency of greater frequency than the carrier signal. As you can see, for 1, it will follow the carrier signal. For 0, it will have a greater frequency. For 1, it will follow the carrier signal. For 0, it will have a greater frequency. So the part of the waveform which have the higher frequency is denoted by f1. and the carrier signal frequency is denoted by F2. So this is what F1 and F2 is represented. And this is the waveform of BFSK. That's coming to the modulation part of BFSK signal. The input binary data, again, it is very simple, consisting of two balance modulator and an adder. So the input binary data is passed through a bipolar non-return to zero encoder. Firstly, it is passed through an encoder. Its output is applied to two independent balance modulators. Let us say this is M1 and this is M2. The other inputs of M1 and M2 are the carrier frequencies which are generated by the local oscillators having frequencies of F1 and F2. The output of the balance modulator are then added together in a linear adder circuit. Its working is very simple, and the resultant BFSK signal will have either the frequency carrier 1 or the 2. As inverter is here, so only one of the signal will be passed. Either F1 will be passed or F2 will be passed. So we will get the respective frequencies at the output. Coming to the demodulator portion, it is again very simple. The main function of BFSK demodulator is to generate the original digital data signal from the BFSK signal at its input. Again, it consists of two balanced modulators followed by an integrator or combination of two correlators and a decision device. So the received BFSK signal is applied to the two correlators, 1 and 2. The correlator circuit basically comprises of a balance modulator followed by an integrator. The other inputs to the balance modulator are the carrier oscillator signals at F1 and F2 frequencies respectively. The outputs of the two correlators are then subtracted and is then applied to a decision device. The decision device compares the input signal with a preset threshold level, which is usually 0 volts. If its input signal level is greater than 0 volt, the detected output is binary 1. And if it is less than 0 volt, the detected output binary is signal 0. Coming to the advantages portion, the transmission bandwidth of BFSK is same as that of ASK. FSK is less susceptible to errors than ASK. It has better noise immunity than ASK. The peak frequency offset is constant and always at its maximum value. The highest fundamental frequency is equal to half the information of the bit rate. Coming to the last portion of last topic of this video lecture, that is QAM, quadrature amplitude modulation. So basically, quadrature amplitude modulation, also known as quadrature amplitude shift key, is a form of digital modulation technique which is much similar to PSK, except the digital information is contained in both the amplitude and phase of the modulated signal. So QAM can either be considered a logical extension of QPSK or a combination of ASK and PSK, both. This is the modulator circuit of the QAM signal. It consists of a serial to parallel converter followed by digital to analog converters and balance modulators, and these are the output of balance modulators are then added to produce a QAM signal. So in QAM, two different signals are sent simultaneously by using two identical copies of the carrier frequency, one shifted by other through a 90-degree phase shift. If one is cos, the other is sent as a sine. The input is a data stream of binary digits at a rate of FB BPS. This data stream is converted into two separate data streams of FB by 2. Again, here FB is sent, one frequency, suppose F1 is sent, and half of these is sent to two portions. F1 by 2 is sent here, and half is F1 upon 2 is sent over here. One data stream is ASK modulated on a carrier frequency FC. Other data stream is ASK modulated by the same carrier frequency which is shifted by 90-degree. The two transmitted modulated signals are then added and then transmitted, and this is how QAM signal is generated. Now coming to the demodulator of this only. It consists of two valence modulators and a carrier is applied. One is in 0 degree and one is pi by 2 shifted, that is 90-degree shifted. Then it is passed through an integrator and a low pass filter. Then it is passed through a A to D converter, and finally parallel to serial converter produces the original output of our matches signal. The QAM or QASK demodulator is similar to the AM array PSK demodulator, except the value of M equal to 4 in carrier recovery circuit. A local set of quadrature carrier signals is recovered for synchronous detection by raising the received signal to the fourth power. And the available quadrature carrier signals are applied to the two correlators, each comprising of a balanced modulator and an integrator. The integration is done over time interval. Symbol synchronizers can be used for synchronization, and the original information bits are then recovered by using the analog to digital converter and a parallel to serial converter. So that's all for the today's lecture. This was the last topic, and we are only left with the QPSK. One full video lecture is needed for that, as the waveforms are very typical for that. We need to understand it very thoroughly. So I'll cover it in the last and the next lecture, which is the last lecture of our lecture series, Analog and Digital Communication. If you have any queries related to this, please comment me on the comment box. Whatever we have discussed today in this lecture, I think it is much easy. Block diagrams are very easy. Their waveforms and block diagram should be made. Without diagrams, there is no topic covered in the ADC. So please be sure that you make the waveforms and the diagrams of each and every topic in whatever paper you are giving. If you have any queries, please let me know, and see you in the next lecture. Thank you. Say Janandam.